We've been discussing sampling distributions in class, and I wanted to just make a video that summarizes what the big idea is. So we're going to have two different variables. We're going to have categorical and we're going to have quantitative. And we're going to be asked questions about what the probability is that this or this happens. How likely is it that this event or this event happens within a sample? So the good news is we can actually use normal calculations to do this. First, let's get our variables straight. If we're talking about parameters, we're going to use the value p. Now, the mean of our sampling distribution will be p, and then we have p hat, which is our sample statistic. Now, we're learning that as long as our sample is large enough, we can use normal approximations. Now, what's large enough? You have to show that you have at least 10 successes and at least 10 failures. And if you can show that, then you can use normal CDF. Now, the same goes for quantitative. Now we're working with mu and x bar. That x written there should have a bar over it. That's your sample statistic. Now, again, we can use normal approximations. If the population's normal, then our sampling distribution is normal. That's a given. However, it's okay if our population's not normal, if it's skewed or if it is uniform. The central limit theorem says as long as our sample is large enough is at least 30, then we can still use normal approximations to calculate these different probabilities. Okay. And now what else do we need to look at? We can't use normal CDF yet and calculate our standard deviation until we see that there's independence between trials. This is needed for probability. But these don't have independence of trials. That's not a reasonable assumption to make. So then what we do is show that the sample's random and that our sample isn't too large. It's less than 10% of the population. With all these things, now we can use normal approximations to calculate the probability. Don't forget, you should calculate your z-score. On your formula sheet, on the AP stat test, it gives you a formula that says your test statistic equals statistic minus the parameter divided by standard deviation. Now for categorical data, you're going to take p hat minus p divided by the standard deviation formula. These things are given to you on the formula sheet. For quantitative data, you take x bar minus the mean and divide by sigma over the square root of n. Isn't this so exciting? We've just shown that we can use normal calculations, normal CDF, even if our population isn't normal to begin with. Now let's look at and examine this population a little bit closer. Say we do have a population that is normally distributed. That would mean we have a sample size of 1. Its center is mu and its standard deviation is sigma. It takes on this normal shape, which I have sketched here using a pipe cleaner. Now, what happens when we increase our sample size from 1 in the population to n equals 4? This is going to create a different sampling distribution. It's like it's getting squeezed in. So the center stays the same. The center that was mu is still the center of our sampling distribution. But now our variance is going to change. Our standard deviation is going to change. We have to divide by that square root of 4. That's why you see a higher peak. The variability, which is our standard deviation, actually decreases by a factor of 1/2. Let's increase our sample size even more. Let's look at a sampling distribution where n is 25. Now this is if we were to take every single possible sample of n equals 25, what would this distribution look like? It's still bell-shaped. It's still centered at the same mu as all the population in any other sampling distribution. But now our original standard deviation is going to be decreased by a factor of 1/5 because we divided by that square root of 25. So what's the moral of the story here? The shape stays the same. We still have this bell-shaped curve that we started with in our population. But as our sample size increased, the variability or our standard deviation, we saw a decrease. I hope this was helpful in understanding the big ideas and the big concepts from Chapter 7.